everyone, welcome to Agri Addict YouTube channel. I am your tutor Sakhi. Today we'll be discussing lecture 4 of Statistics lecture series Introduction to Experimental Designs. This is my short intro. I have done my undergraduation from JNKVV Jabalpur, currently pursuing masters at IRI Hyderabad Hub Creda, Department Agronomy. I have secured All India rank 12th in ICAR PG 2024 examination. So let's start with the lecture. So first we'll discuss the basic principles of field experiments. Why we need these basic principles? Because if we are going for a field experiment, so that field might be heterogeneous in nature. And generally this heterogeneity will be in terms of soil fertility. Because when we are taking a field for experiment, so the fertility might vary. Okay. So for say, if we are assuming that fertility is varying in that direction. So this is a low fertility zone. And this is a high fertility zone. Fertility is varying from here to here, from left to right. So this is the heterogeneity. So this will result in the generation of experimental error. Experimental error. This experimental error will disturb our accuracy of result. So what we have to do, we have to minimize this error. For minimizing this error, we need these three principles, okay, which we are going to study. So generally, variations observed in field experiments are due to soil fertility. Experimental fields lack homogeneity. Of course, it is heterogeneous because we cannot say that if it is a per se 1 meter square area, so this area will be having heterogeneity in terms of soil fertility. Even the soil texture also sometimes changes between two fields. If we are moving from one field to another, the soil texture also, maybe this is clay, this might be sandy soil or sandy loam, like that. So like that, fertility also varies within the field. So that will result in the generation of experimental error. When we are talking about the variations which we are having on the field, which we get in the field, can be due to treatments which we are using, plus the experimental error due to the heterogeneity in field. So these two are the source of variation in the field. First will be the treatments which we are using, and the second will be the experimental error. Let's move and let's study the three principles. So first principle is replication, second is randomization, third is local control. What is replication? Replication is the repetition of treatments. It is the repetition of treatments. We'll be repeating the treatment so that the experimental error should not be more. It should be less. We have to minimize the experimental error. So that's why we will repeat the treatments so that we can get the exact performance of those treatments which we want. Okay. So replication is used to estimate the experimental error. The objective of replication is to estimate the experimental error. Generally, in field experiments, we go for 3 replications, and we can also take 4. But why we are taking 3 replication is, in 3 replication, we generally get correct results, and the complexity will be less. If we're increasing number of replication, if we're increasing, then complexity will increase. So it will be difficult to conduct the experiment. The second principle is randomization. What is randomization? Here, each and every treatment should get equal chance to get allocated in natural variation. The way we are putting treatments into that field, or say this is the field, and we have made 3 replications. Okay. And now we have to put 4 treatments in that. So this is replication 1, replication 2, replication 3. So 3 times the treatments will get repeated. For say we have 4 treatments, T1, T2, T3, T4. So what we'll do in the first replication, we'll randomly allocate so that each treatment has equal chance to get allocated in any particular plot. For say in R2, we are keeping T1, T2, T3, T4 randomly. So randomly if we are putting, so this is called randomization. Each treatment, each and every treatment should get equal chance to get allocated in natural variation. So what is the objective or what is the role of, what is the use of randomization? It provides us the valid estimation of experimental. Here we studied that it provides an estimate of experimental error in replication. But randomization provides us valid estimate of experimental error. Third principle is local control. So what is as the word says, control. So here we are controlling the experimental error. So it minimizes the experimental error. In the next slide, I'll explain you what does it mean. So let's move. First, this is the field. We have to conduct an experiment here. And we know that the fertility is varying in this direction. Here it is low fertility and here it is high fertility. Okay. So what we'll do to make this field homogeneous, because as we know it is heterogeneous. Okay. So what we'll do, we'll do blocking. We will make blocks. This is the high fertility zone, block 1. Medium fertility zone, block 2. And low fertility zone, block 3. Okay, like that. What we did here, that this is the one block, this is the second block, and this is the third block. So here, within the block, there will be homogeneity. And between the block, for say this between B1 and B2, there will be heterogeneity. So in the previous slide, what we studied is that it minimizes experimental error. It controls experimental error. Here how we are controlling. We are categorizing the field into 3, like low fertility block, medium fertility block, and high fertility block. Like that, this block 1 will be referred as replication 1. Okay. Block 2 as replication 2. Block 3 as replication 3. Okay. Now we have for say we have 4 treatments, T1, T2, T3, T4. And now we'll make 4 blocks. 4. Okay. So first is that replication. We are repeating the treatments. So we have 4 treatments, and now we have to do randomization. We will randomly allot. We are putting T1 here, T2, T3, T4. Randomly we are putting. Here also we are putting T1, T2, T3, T4. T1, T2, T3, T4. Here randomly we are putting because we don't know in which block which treatment will be coming. So that's what in the previous slide it is being told, that each and every treatment should get equal chance to get allocated in natural variation. So no treatment will get any profit, like if we want to put like T3 in a very good plot having a good soil fertility like that. Here everything is randomized. Nothing, we are not supporting any one treatment or favoring any one treatment. So that's why randomization is the second principle. And first we studied that local control to reduce the experimental error. And third is this replication. This replication, first we are putting all the four treatments in one replication, then again four treatment in the second replication, again four treatment in the third replication. So here what we are doing in replication, we are repeating the treatments. I hope you understand why we follow these three principles: replication, randomization, and local control. Let's move to the next slide. So to have a valid estimate of experimental error, principle of replication and randomization is used. This is very important. This can be asked, like, to get a valid estimate of experimental, what are the two principles which are used? So it will be replication plus randomization. This can be directly asked in JRF kind of examination. So to reduce experimental error, the principle of replication and local control is used. When we have to reduce the experimental error, so in this case, what we are using is replication plus local control. Okay, I hope you got the point. Let's move to the next slide. So we will be discussing the commonly used experimental designs. So first is completely randomized design. In completely randomized design, the most important character is here no blocking is done. Here blocking is not required because the experimental units are homogeneous. Completely randomized design is not used in field. If it is not used in field means it is not having any kind of heterogeneity. The experimental units will be homogeneous. If homogeneous it will be, then no blocking is needed or no local control is needed. Because we in the previous slide we studied that local control is needed where there is heterogeneity. If here we are saying that homogeneity is there, then we need not to do blocking. Okay, because blocking we are doing only to reduce heterogeneity. So the CRD, completely randomized design, is used in lab, greenhouse, and glasshouse. Okay, so these 3 points you have to remember. First, there is no blocking. Second, the experimental units in completely randomized design is homogeneous. It is not used in field, used in lab, greenhouse, and glasshouse. So next design is randomized complete block design. Used when there is a single factor to study. For say, we want to study nitrogen. Nitrogen a single factor or a phosphorus. So there might be different level like 20 kg nitrogen, 40 kg nitrogen, 60 kg nitrogen per hectare. So these are the three doses, three levels of nitrogen. It might be nitrogen or phosphorus like 20, 40, 80 kg per hectare. Okay, this is used in field, but the CRD is not used in field. So this can be used in field, means it can be used in heterogeneous field. And if the field is heterogeneous, here blocking will be there. We have to do blocking because we have to reduce the heterogeneity in the field. Let's move to the next. So third is factorial randomized block design. Factorial design we generally use when we have to study two or more than two factors. When we have to simultaneously study two or more than two factors, like we are studying nitrogen also along with phosphorus. So two factors are there. More than two also we can study. So if we want to study two or more than two factors, then we use factorial randomized design. And the most important character of factorial randomized design is we can study interaction effect also. For say this is the first factor, nitrogen and phosphorus. And nitrogen and phosphorus together, what they are producing, what effect they are producing, we can study. We can study the interaction of nitrogen with phosphorus. If we are giving 0 kg nitrogen, or we are not giving 0 means not giving nitrogen and 0 kg phosphorus, there's single effect, and when we are giving no phosphorus, no potassium, what is the effect? Then if we are giving 20 kg nitrogen and 50 kg phosphorus, then what is the effect of these two together? We can study the interaction. Okay. The next is split plot design. Split plot design is used in two factors. When we are studying two factors in which one factor require large plot and second factor requires small plot. What kind of factors which require large plot? Like tillage. If we want to study different tillage like zero tillage, conventional tillage, reduced tillage. So if we want to study the effect of different tillage, so then we require large plot. Why? Because if we are making plot of this size, the tractor will not move in this small plot. So we have to make a big plot for it. So that's why tillage. And second is irrigation. Because in irrigation, for say, we are making 4 plots of small sizes, and here we are giving furrow irrigation, here we are giving wild flooding, here we are giving drip irrigation, here we are giving sprinkler irrigation. So this furrow irrigation and this wild flooding, the water will seep from one field to another. Then the experiment will not be accurate. So that's why for irrigation also we need large plot. Okay. And small plot, generally we use for nitrogen dose, phosphorus dose, sowing time, like that, plant population also. We go for small plot. When the factors are this, like nitrogen dose, sowing time, we use small plot. And when we have like we have to do tillage, irrigation like that, for that we need large plot. So two factors. If there are two factors to be studied, in which one is requiring large plot, another is requiring small plot, then we go for split plot design. Here, the accuracy in results are less than factorial RBD. The accuracy will be less than this factorial RBD in split plot design. Okay. Next, split plot design. For say, we have made this big plot, large plot. Here we are doing tillage. And in this plot is divided into subplot. And this again is divided into subplot. So for say, this large plot, here we'll be studying three factors. First is requiring large plot, second is requiring small plot, and third is requiring very small plot, like subplot. So for large plot like tillage irrigation, as I told earlier, subplot for say plant population, sowing time, subplot nitrogen dose, phosphorus. When we have to study three factors simultaneously, then we use split plot design. Okay. The sixth design is strip plot design. It is also used to study two factors, just like split plot design. Here, the factor require large plot. For say tillage, here both the factors are requiring large plot, like tillage and irrigation. If we want to study these two factors together, both are requiring large plot. So here one will be set as horizontal factor, second will be set as vertical factor. Okay. Here both the factors are requiring large plot, but in split plot what we studied in the previous slide, we studied that here one factor is requiring large plot, another factor is requiring small plot. But in this case, both the factors are requiring large plot. Okay. Tillage, irrigation. When we have to study these two factors together, then we'll go for strip plot. One will be regarded as horizontal factor, another will be regarded as vertical factor. Let's move. So seventh design is Latin square design. When variation or fertility gradient is bidirectional. When we have a field, for say this field we have, and we know that this field has variation. Here it is high fertility zone, this portion, and when we are moving to the right side, it is having low fertility. So it is one direction, and then here on the upper side, it is having higher fertility, and when we are going downside, it is having lower. The variation is in two directions. So this is the design. Latin square design is used when the variation or fertility gradient is bidirectional. So this can be asked as a question: when variation or fertility gradient is bidirectional, which design is used? Then it will be Latin square design. Here it is most important is the number of treatments and the number of replication are equal. Means T is equals to R. Okay. Here rows and columns are used. This is also an important point. Rows and columns are used. What we have to remember is the number of treatment is equals to number of replication. When the variation is bidirectional, then LSD is used, Latin square design is used. So here I have included one point is when variation or fertility gradient is one directional or unidirectional, then what designs we can use? It will be RBD and factorial RBD. When the variation is when variation is unidirectional, then we'll be using RBD and FRBD. Next. So next is completely randomized design. We will study it in deep. So here the maximum error degree of freedom will get in completely randomized design. As we studied earlier, experimental unit here is homogeneous and limited. There will be no heterogeneity. And this design cannot be used in field. This can be used in lab, greenhouse, glasshouse. Okay. So what are the merits of completely randomized design? Unequal number of replications can be used. Here, for say, we are taking this gibberellic acid dose, 20 ppm, 40 ppm, 60 ppm, like that. And we want to see the effect of this GA on plant tissue growth. Okay. So this 20 ppm, we can make 4 replication. For this 40, we can make 6 replication. It depends on us. And for 60 ppm, we can make 5 replication. It depends on us. We do not have to keep replications equal for each treatment. We can keep different replication for different treatment because here the replication is not a source of variation. In CRD, replication is not a source of variation. So that's why lost replication experiment can be analyzed by remaining application. For say if we from this 4 replication we lost one replication and we are left with only 3 replication, then also we can carry out our study. Why? Because replication is not a source of variation. If there is loss in replication, then also we can go for the study. That is the merit for this completely randomized design. Okay, then let's study the demerits. Any error in experimental units will result in loss of accuracy of experiment. So if there is some error or some heterogeneity seen in the experimental unit, then the accuracy will be lost in CRD. So that's why we do not go for field experiments. CRD is not used in field experiments. Okay, let's move to the next. So we will study the analysis of variance, ANOVA. This ANOVA is given by R.A. Fisher. Okay, R.A. Fisher gave this ANOVA. So first, this ANOVA table, this is the ANOVA table, I'll explain you this. So first column is source of variation. Second is degree of freedom. Third is sum of square. Fourth is mean sum of square. And fifth is F value or variance ratio. So here the source of variation, as in the previous slide I told, here the replication is not a source of variation. Here what is the source of variation? The treatment which we are taking will be the source of variation. The error that might come in during conducting the experiment and the addition of these two, the total. Okay. And the degree of freedom is what? For say for treatment, We have to find degree of freedom. So we just have to do t minus 1. That will be a degree of freedom. For error, what will be? T into r minus 1. This is the degree of freedom to calculate the error degree of freedom. Okay. And then total will be the RT minus 1. So number of plots will be R into T. Okay. This is the total. So RT minus 1. This is the total degree of freedom. Now sum of square. What is sum of square? Sum of square we calculate through a formula when we have data. Then it is having some different formula to calculate sum of square of treatment, sum of square of error, and like that sum of total sum of square. So this we need not to know for JRF. You'll study this in MSc as experimental design course. Then you'll get to know that how when we have a data, then how we have to put this values in formula, and then we'll get the sum of square. In this, you just have to remember that sum of square is there. Sum of square of treatment we'll calculate when you'll study in further. But in JRF, this will not be asked. You simply will get questions like calculate error degree of freedom, like that t into r minus 1. T and r will be given and you have to calculate that. Like that, then they will be giving question. Now the second is mean sum of square. Mean sum of square, how we'll calculate? Mean sum of square is sum of square divided by degree of freedom of that. For say we have to find mean sum of square of treatment, then we'll do sum of square of treatment divided by degree of freedom of treatment, t minus 1. Like that, if we have to find mean sum of square of error, then it will be sum of square of error divided by t into r minus 1. And if we have to find f value or variance ratio, what we'll do mean sum of square of treatment divided by mean sum of square of error. So we will divide this mean sum of square of treatment by mean sum of square of error. That's how we'll get the f value. Okay. I hope you got. In this, you have to remember this degree of freedom of error treatment, how we have to calculate. This will be asked because they will give you number of treatment, number of replication, and you just have to find the error degree of freedom or treatment degree of freedom, just like that. So next, here I have included one question. So question is cytokinin we have given 1, 2, 3, 4, 5 doses, 10 ppm, 20 ppm, 30 ppm, 40 ppm and 50 ppm. Okay. So number of replication R is given to us. R is equals to 4. And treatments are how many? 1, 2, 3, 4, 5. So treatments are, number of treatments are 5. Now it is being told to us to find error degree of freedom. So we have to find error degree of freedom. So what is the formula? T is equals to R minus 1. In the previous slide we studied here. T is equals to R minus 1. So put the value of T, it will be 5 in bracket 4 minus 1. It will be 5, 3. 5 3 is a 15. So error degree of freedom will be 50. These kind of question you will be asked in JRF examination. Next, randomized complete block design. It is the most commonly used experimental design. Randomized complete block design is used for treatments less than or equal to 20 treatments. If we'll be using more than 20 treatments, there will be less precision. So this RCBD, if we are using it less than or equal to, when we are using it for less than or equal to, it will give high precision. If we are increasing treatments more than 20, then precision will be lost. So generally it is used up to 20 treatments, randomized complete block design. So if any plot is destroyed by any means, missing plot technique would be used to analyze the experiment. For say, this is the plot. And we have 5 treatments, T1, T2, T3, T4, 5. And now we have this fertility variation. Here it is low fertility. Here it is high fertility. To minimize the error, what we'll do? We will make blocks. This is the block. We will name it R1, R2, R3. Now the second principle, first principle we did, replication. Blocking also we did, that is third principle, local control. Second principle is randomization. Now we have 5 treatments. So we will make 5 boxes for it. Okay. Now we have to use randomization. Okay. So we will randomly allocate treatments like T1, T2, T3, T4, T5. Here in the second, T1, T2, T3, T4, T5. In the third also we can randomly allocate T1, T2, T3, T4, T5. Like this we will make the plot. So if any of the plot is destroyed by any means, here we have to use missing plot technique. In CRD, we said that replication is not a source of variation. But here, if we'll see the ANOVA, here the replication is a source of variation. So if one of the plot is missing, for say somehow we lost this plot, so we won't be able to get the results. So we have to use the missing plot techniques to analyze the experiment. Okay. So let's move to the next slide. So here the source of variation, there are replication is also a kind of source of variation, treatment, error, and the total. So degree of freedom to calculate replication degree of freedom will be R minus 1, simple. Treatment T minus 1. Error will be R minus 1, T minus 1. This you have to remember. This can be asked in a question. And total will be RT minus 1 as in the previous slide. Sum of square will be sum of square of replication, sum of square of treatment, sum of square of error, and then total sum of square. Mean sum of square will be sum of square of replication divided by degree of freedom. Sum of square of treatment divided by degree of freedom. Sum of square of error will be divided by R minus 1, T minus 1. So how we'll calculate F value? We have to divide the mean sum of square of treatment by mean sum of square of error. So here the total variation would be due to replication, treatment, and error. Okay. Let's move to the next slide. Here, factorial randomized block design, here it is used when we have 2 factors or more than 2 factors. Here, blocking is done perpendicular to the gradient. Here, the gradient is in this way. Then what we'll do blocking it perpendicular to the gradient. See, perpendicular. So we'll make replication 1, replication 2, replication 3. Okay. For say this 2 factors I have given, nitrogen dose 50, 100 and 150 kg per hectare. So it is 3 doses. And like that phosphorus 20, 40, 60 kg per hectare, 3 doses. If we are multiplying, so this is the factor. There are 3 terms, factor, treatments and levels. So factor is this nitrogen and phosphorus. These are the 2 factors. And levels are that nitrogen at 50 kg level, 100 kg level, 150 kg. So these are the levels, 1 level, 2 level and 3 levels. Nitrogen is given in 3 levels. And phosphorus is also given in 3 levels. That is 20 kg, 40 kg and 60 kg. And what are the treatments? When we multiply this 3 by 3, that both the levels of 2 factor, then we'll get 9 treatments. So how we'll get 9 treatments is, I have written this T1 to T9. So it will be when we are pairing 50 kg nitrogen with 20 kg phosphorus, 50 kg nitrogen with 40 kg phosphorus, again 50 kg nitrogen with 60 kg phosphorus. So the T4 will be 100 kg nitrogen plus 20 kg phosphorus, 100 kg nitrogen plus 40 kg phosphorus, then again 100 kg nitrogen with 60 kg phosphorus. Like that, the third level, that is 150 kg nitrogen with 20 kg phosphorus, 150 kg nitrogen plus 40 kg phosphorus and 150 kg nitrogen plus 60 kg phosphorus. So that's how we make 9 treatments. And these 9 treatments we have to allocate in 3 replications. How much it is? 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we'll be arranging randomly. T2, T3, T4, T5, T6, T7, T8, T9, like that. In the first replication, we arrange all the treatment. Now we have to repeat the treatments in replication 2. T1, T2, T3, T4, T5, T6, T7, T8, and T9. Like that here also T1, T2, T3, T4, T5, T6, T7, T8, T9. Randomly we are allocating throughout the field. First, you have to remember this factorial randomized block design is used when we have to study 2 factors or more than 2 factors. Here, blocking is done perpendicular to the gradient. If gradient is in this direction, we will do blocking in this direction. So, what is our aim is to minimize the heterogeneity within the field. Minimize the heterogeneity within the field. Okay. Next, analysis of variance for 2 factors. It will be the same just like RBD. Replication, degree of freedom will be R minus 1. Treatment, A into B. That nitrogen and phosphorus is regarded as A into B. So first factor A is, the degree of freedom for it will be A minus 1. Factor B, B minus 1. And when we are getting, I said in the previous slide that factorial randomized block design is very good to study the interaction. Here we can get the interaction also. But in randomized block design, we can't get interaction because we are only studying 1 factor. Here we are studying 2 factor and we are getting interaction also. So for interaction, the degree of freedom will be A minus 1, B minus 1. So error degree of freedom will be R minus 1 into AB minus 1. Total degree of freedom will be RAB minus 1. Similarly, sum of square of replication, sum of square of treatment, sum of square of A factor, sum of square of B factor, and sum of square of A and B in an interaction. Then some error sum of square and then total sum of square. Like that, mean sum of square will calculate sum of square of replication minus R minus 1. That is degree of freedom of replication. Then sum of square of treatment. Then AB minus 1. Sum of square of A factor, it will be A minus divided by A minus 1. Then sum of square of B divided by B minus 1. Sum of square of A into B, that is interaction, divided by A minus 1, B minus 1. Like that, for factor A, we can calculate the F variance ratio. It will be mean sum of square of A divided by mean sum of square of error. FB will be mean sum of square of B divided by mean sum of square of error. FAB, that is interaction, if we have to find the F value, then we'll do mean sum of square of AB divided by mean sum of square of error. So this is for 2 factors. This is for 2 factors. ANOVA for 2 factor in factorial RPD. So next is ANOVA for 3 factors. If we have 3 factors A, B, and C, then here the source of variation will be replication, R minus 1 for it. And then 3 factors, factor A, factor B, factor C. So here will be A minus 1, B minus 1, C minus 1. And now we have to study the interaction. So how the pair will be A and B's interaction, A with C's interaction, B and C interaction, and A, B, C interaction. So here we can get 4 kind of interaction. So for these 4 interactions, what will be the degree of freedom? It will be A minus 1, B minus 1 for A into B, A minus 1, C minus 1 for A into C, B minus 1, C minus 1 for B into C, and A, B, C for it will be A minus 1, B minus 1 into C minus 1. So error degree of freedom will be R minus 1, and it will be, here some correction might be there, is A, B, C minus 1, because here it is 3 factors. So correct it. And then total for it will be R, A, B, C minus 1. This is how it will be. Okay, correct it. So next, let's start with the questions. In which design replication is not a source of variation? I previously told that in CRD, replication is not a source of variation. So let's move to the next question. In RBD, there are 10 treatments, pre-replication, the degree of freedom of error. So now we have to find error degree of freedom. So it will be R minus 1, T minus 1. This is the formula to calculate, which I told earlier. So here the treatments is 10 and replication is 3. So now just we have to put the value 3 minus 1 and T minus 1 will be 10 minus 2. Okay, now 2 into 9, it will be 18. So error degree of freedom will be 18. So correct option is D option. Like this, they will be asking question because in JRF examination, they will ask simple questions like this because they will not ask lengthy question because it can't be asked in MCQs. Analysis of variance is one of the statistical tools developed by Dash, Spearman, Carl Pearson, Professor R. A. Fisher, or Galton. Just I told previously it is R. A. Fisher. Very important to remember it. Which of the following designs have one error only? So here CRD, RBD and FRBD have single error. When we'll study other designs like split plot, strip plot, they have more than one error. Okay, so these are the three designs which are having only one error. Okay, thank you so much.